Hello, and welcome to the Data Engineering Podcast, the show about modern data management. Data migrations are brutal. They drag on for months, sometimes years, burning through resources and crushing team morale. Datafold's AI-powered migration agent changes all that. Their unique combination of AI code translation and automated data validation has helped companies complete migrations up to 10 times faster than manual approaches. And they're so confident in their solution, they'll actually guarantee your timeline in writing. Ready to turn your year-long migration into weeks? Visit dataengineeringpodcast.com/datafolds today for the details. Your host is Tobias Macy, and today I'm interviewing Dan Sotolongo about the challenges of incremental data processing in warehouse environments and how delayed view semantics help to address the problem. So, Dan, can you start by introducing yourself?
Yeah, sure. Thanks for having me on, Tobias. My name is Dan Sotolongo. I'm a principal engineer at Snowflake, where I've been working for the last 5 years to try to make kind of data engineering easier for people.
And do you remember how you first got started working in data?
Yeah. So I guess I started coding way back in middle school, but it wasn't until my undergrad when I studied physics and computer science, and kind of at the intersection of those two, we would do a lot of data analysis for physics experiments. And so it was kind of there that I cut my teeth using like NumPy and like IPython back when it was called IPython. Also used a lot of Mathematica, but that's kind of gone by the wayside since then, since I don't have a free license anymore. uh,
It's funny how many people I know who started in physics and ended up in software.
yeah, there's a lot of gravity to it.
Absolutely. And so, in terms of the conversation for today, I'm wondering if you could just start by giving your definition and your scoping for the term incremental data processing, because it can be applied to a lot of different contexts.
Yeah, that's true. And I mean, from the highest level, I feel like it starts with the data processing, right? And what I tend to focus on, or I called it data engineering just now. I tend to focus on a context where you have some kind of continuous source of data that's it doesn't have to be big, but it can potentially scale up, right? If we're talking about Snowflake and cloud data warehouses, that's a lot of the point. But the kind of continuous nature is also really important because if you don't have a continuously changing data set, then a lot of the problems just kind of get simplified and don't really matter, right? So when you have that continuous evolving data set, that could be through like an append only kind of situation where you're just like adding events to the end of some log, or it could be like a table, something in your OLTP database that is being updated continuously. Very often you want to take that source of data, move it somewhere else, transform it into some structure that makes it more easily queryable and analyzable. And kind of like the naive, easy way to do that is you just dump everything. You do everything every time, I guess. Anytime you want a new update, you run your entire transformation pipeline over all of your data. But as you can imagine, that is insufficient very quickly, both because of cost, where you're using a lot of resources that you don't need to, but also in terms of latency. Like if you have to do everything before you get an updated result, you have to wait around for a while. And so the incremental adjective there, what it refers to is trying to do like the smallest amount of work you can do in order to bring your results up to date, kind of all the way from the sources, kind of propagating it through all the different steps you might have to do. And those steps might start with like extracting data from a source, loading it into a data warehouse like Snowflake, doing a bunch of transformations, whether those might be like joins or aggregations or lookups, all kinds of things you might want to do. And then potentially you might even want to do this within the analytics layer to kind of maintain the results that you actually want to query and get really low latency.
A lot of the problem statement there in terms of incremental and the unbounded data sources is very reminiscent of a lot of the conversation that happens around streaming data workflows where you're dealing with something like a Kafka or a Flink and you want to do the incremental data loading or incremental data processing in that streaming engine, which obviously brings along with it a lot of operational overhead and technical complexity. And I'm curious how you think about the Venn diagram of the problem statement that you're discussing in terms of incremental data processing, particularly with the context of a data warehouse system or some sort of tabular analytics, and the use cases for that more continuous stream processing element that a lot of people are using the things like Flink, Spark Streaming, et cetera, to apply to.
Yeah, that's a good question. And I feel like the industry as a whole hasn't really come to a solid consensus around all of this yet. But the way I look at it is, so I like to start with like, what are you trying to achieve? And usually that's like get some data from any number of sources, getting it to a smaller, hopefully, number of destinations, and doing some transformations either along the way or in the destination system. And once you have that high level description, you can kind of think about, okay, what are my non-functional requirements here, right? Like, what freshness do I need for my results? What kind of resource efficiencies do I need? How many people can I allocate to this in the first place, both for development and maintenance, right? And that's where the engineering really starts getting in. You have to like figure out the trade-offs between these things. And that's when you really need to kind of tease apart the Venn diagram. And the classic distinction is batch systems and streaming systems, right? And the way that people would think about this is like the batch systems are more efficient generally. They're kind of easier to maintain, but I guess I've always had the sense that they're kind of unsatisfying from like a theoretical perspective, where it feels like you're kind of instrumenting this or orchestrating this kind of complex machine that it really feels like what you're trying to do is really simple. And streaming systems, they have this like abstract aesthetic appeal where they give you a programming model and you don't have to reason about like the crazy machine and that you're all the pieces that you're moving around. But then in practice, they tend to be like a huge pain to actually use, right? And so I think that that's like the traditional Venn diagram. But I think what's been missing is some way of pushing out this trade-off between like what seems hard but is actually easy, and what is hard but seems what seems hard but is easy, and what seems easy but is hard. And that's kind of where I think kind of the more recent crop of incremental view maintenance engines have been trying to step in, where the idea is you don't actually need this really complicated programming model that a lot of like the flinks and the data flows and the kind of 2010s, I would say, era of stream processing came with, but rather you can just specify like, here's the result that I want on some source data, and leave it to the engine to kind of keep that thing up to date for you. But even within that specification, you can, within the implementation, make a whole bunch of trade-offs around efficiencies and latencies. And so even though you have a large number of systems that are focused on kind of low latency stream processing, that paradigm still applies in what would traditionally be handled by batch. And that's kind of where Snowflake has put our stake in with the dynamic tables feature, where it's a micro batch engine under the covers, but the programming model is a streaming programming model, which means you don't have to think about orchestration and like keeping things up to date, thinking about progress and all those things. It kind of handles it for you. But the idea is we're targeting kind of higher latencies, not like 1 second, but rather a minute, or all the way scaling up to like hours if you want to get the efficiencies from that.
And in terms of the approaches that data engineers have taken in pursuit of incremental data processing, we've already touched on some of the pure streaming use cases. But even within the context of tabular analytical data, there have been a number of different technologies and architectures that have been put forward and that people are employing. And I'm wondering if you can talk to some of the common patterns that you have seen engineers and engineering teams apply to this problem space, and some of the common challenges that they run into in the implementation of those different patterns.
Mm-hmm. Yeah, and I guess this dovetails nicely with what I just said. We've got like the traditional Venn diagram of like batch systems, where what you tend to do is you'll have your orchestrator in Airflow or Dexter or something like that that kind of does things on a periodic basis. And the things that it does, you kind of have to figure out yourself, right? Like you might say, look up the most recent chunk of data, do some transformation, put that in another table. And that works totally fine if you're kind of doing it at a relatively low frequency. But it gets really hairy if you try to crank the latencies up, both because the orchestrators weren't designed for that, but also like just reasoning about the consistency of your results gets really, really tricky. And so that's what the traditional stream processing kind of half of the Venn diagram has been about, where instead of having like they kind of absorb the scheduling complexity for you, and they give you this more complicated programming model and an implementation that implements that, right? But then they also run into all these operational challenges where they have like large amounts of state, and they have distributed checkpointing algorithms and like a whole bunch of tuning knobs that you might have to figure out. Some of the programming model concepts might be tricky. I used to, like, before I was at Snowflake, I worked at Google on streaming data flow, and we spent a lot of time trying to explain like watermarks and triggers, which are kind of really important concepts to express what you need to express, but it can take people a while to kind of wrap their heads around it. Yeah, so I guess those tend to be the two main patterns. And but the big challenge, I guess, that I've never liked is you have to make the decision up front usually, right? You have to say, oh, we're going all in on the streaming thing, and it's going to be hard, but we're going to do it because it's important, or we're going to, play it safe, keep the batch system around. But then, if your latency requirements change or some new use case comes along that actually would benefit from a few seconds of freshness, then you have no way to meet that requirement, right? And so I think the place that we're all trying to head is, don't force you to make that decision up front. Make it so that you can kind of specify what you need, and then make the trade offs later depending on the requirements that come in.
Another approach or another category of technologies that I've seen come in to try and manage some of that technical complexity and present it in a way that is more approachable are systems such as Materialize or Feldera, where they give you a SQL interface and Pipeline DB several years ago, but you still need to have some streaming data source that they are going to feed off of, which is usually a Kafka queue or something like that. And I'm wondering, what are some of the elements of the way that they're approaching the solution that you see as being insufficient for the ways that you would like to see the problem solved?
Hmm. Well, I guess the it's not about insufficiency. I feel like what you end up with when you actually try to implement these systems is you have to make decisions, architectural decisions up front, that kind of target a specific kind of region of the problem space, right? And Materialize and Feldera are both like really interesting, well architected systems that are targeting a specific kind of region of the problem space that focuses on low latency. And so what does that imply, right? That implies they have to build indexes for kind of basically anytime you want to do a join, you need an index in order to make the join happen efficiently. Um, they That means they have to keep around state, but just I think because of the realities of the market that they're in, they can't be the database. They're not the source of truth. They're a processor, and that means that they kind of have to reprocess data in order to repopulate that state if they need to do a backfill, or you need to deploy some new pipeline. And so there are some limitations that you in terms of what you can actually do in that niche, right? And so what dynamic tables does is it takes a completely different approach of be part of the database, and the database here is Snowflake. But in general, this approach works fine, kind of regardless, as long as you are either a source of truth or a repository, I should say, like a repository for the data. Then you kind of have these intrinsic advantages in terms of, like, the data is just there. You kind of see, you can observe the workloads that are already running over it, and you can have kind of synergies between the way that the data is stored and what you need to do on top of it. And so dynamic tables kind of leans into that, and it just reuses kind of everything in Snowflake that we could, and kind of weaves them together in a way that gives you a micro batch incremental processing system that is just natively inside of your database.
And digging into dynamic tables, I know that the generalized pattern behind it is something that you termed delayed view semantics. And I'm wondering if you can talk through some of the details of what that is and some of the story behind how you came to that as a solution to this problem space, and some of the specifics of why that is a reasonable approach when operating in that sort of cloud warehouse context.
Yeah, sure. So delayed view semantics, fundamentally what it is a theoretical framework for making it possible to talk about the semantic guarantees that you want out of these data pipelines. And like I said, it's a theoretical framework. It's about semantic guarantees. Like, there's a whole like decades of work on in this space. So everyone's probably familiar with ACID in kind of the database context. In the distributed systems context, we have our various consistency models, like linearizability and sequential consistency, eventual consistency. So all of these things exist, but when you're kind of shifting perspective into a continuous processing pipeline, they kind of fall short. And the reason they fall short is that most of the time, you don't actually want these pipelines to be like perfectly up to date, right? When you're in an application context and you're doing transactions against your database, it's really important that like everyone sees the same state, and that's what ACID and consistency is all about, right? But in the context of data engineering, most of the time what you're doing is kind of deriving insight from some source of truth that's way upstream. You're not doing like this kind of back and forth interactive workload. And in that context, your freshness requirements go way down, and you want to introduce delays, right? You get massive efficiencies from not having millisecond level latencies in your analytics dashboard, right? And so people do this, right? But the problem is we don't have a way, a kind of unified theoretical framework that lets you talk about both in the same context. Like what ends up happening is if you try to express delay inside of, for example, like your Postgres database, what you really end up saying is, oh, I have weak isolation, right? Like all I'll guarantee is that you read committed data from some point in time, and that's it, right? And it turns out that's just not precise enough. Like you actually, when I say delay, I mean like delay in a very specific way. I mean, like I want my result to be self-consistent, for example, but it's okay if it's 5 hours old. And if you actually take a look at the way that ACID and I'll leave aside distributed consistency because our focus is really ACID. If you look at how isolation is modeled formally, you realize that there is actually no way to have your cake and eat it. That is, have delays and still be able to make precise statements about your your isolation level. And so we kind of ran into this by accident, right? Like we designed dynamic tables. We knew what we wanted to build. We knew what customers wanted, and we've had a lot of market validation that we built the right thing. But then we, 4 years later, or I guess dynamic tables has been GA for like a year and a half or so, maybe almost two. We're writing a Sigma paper, and we're trying to like say, okay, these are the semantics of what dynamic tables do, and trying to model that formally, it just like couldn't do it. And so as part of that paper, we decided, okay, well, we know that this is an important thing to express, and the theory can't express it, so we'll just try to find the cleanest way to express it. And what we ended up doing is like a really small extension to the ACID model that makes it possible to talk about delay and be precise about what you get.
And in that context, both for the generalized delayed view semantics theoretical framework and the specific implementation of dynamic tables, what are the problems that you are explicitly not addressing in that framework?
Yeah, so I guess there's kind of two angles you can take on that question. One is, what does delayed view semantics not address in the first place? I mean, it's a theoretical framework. All it does is kind of give you a common language for everyone to communicate about what you're doing. It doesn't force anyone to implement anything in particular. Like read committed still makes sense in the context of delayed view semantics, and so does serializability. But it lets us talk about what are the actual guarantees you offer in which situation. The other angle is like, what about pipelines that implement delayed view semantics? What can they do, or what can they not do, more importantly, right? And fundamentally, that limitation it's kind of in the word. View semantics means your pipeline is going to produce the result of a view, right? And what a view is a kind of point in time view of the source data. And that means that, for example, you can't like remember data that's been deleted. You can't ignore changes to the source data. There's a whole family of use cases that kind of need to step outside of view semantics, delay or not. And delayed view semantics just can't get you there.
Delayed view semantics and the overall concept of views in database context have a long history. They are typically used as a not necessarily compute efficiency, but a cognitive efficiency of not having to create a whole separate table and manage the data transition from that. You create a SQL statement that maybe joins together multiple different sources and gives you a representation of that you can refer to concretely without having to type out the same query every single time. And I'm wondering if you can talk to some of the ways that the use cases of traditional views, materialized views, and delayed view semantics are gradations of the same problem space.
Yeah, I think the way you presented it is I agree with, which is views are really like about modeling things and making it easier for you to reason about them. And once you have the view, like kind of the cognitive burden problem has been solved to the extent that I want to solve it right now, right? And then materialized views end up being like an operational extension of that, which is make it fast to query, right? In some sense. And delayed view semantics is really just a way of talking about materialized views and what they actually have. Because if you look at the various implementations of materialized views that different systems offer, because most databases have some form of materialized view, you'll notice that the guarantees are all over the map, right? Some really sophisticated databases will give you like really low latency, inexpensive incremental view maintenance of your materialized views. Some of them will schedule the updates for you, and some of them will just say, "Nope, you're on your own. You're going to kind of like Postgres, at least until recently, the only way to do materialized view was you had to issue a command to refresh the whole thing, which locked the whole materialized view. And it would usually, I don't know the details of this, but I think it would almost always do a full refresh, right? This is something that's changing, but in the absence of a common language to talk about it, people would just say, "Oh, materialized view," and as if that actually was a specific answer. And now that I think it's been recognized for a while that materialized views are a really good way to think about continuous transformations. And so we've had these systems kind of being built to make it possible to use the concept of a materialized view in different contexts. But now that we have all this whole, I guess, cornucopia of different systems and different semantics, we need a way to talk about them and how they relate to each other.
And so, digging into the technical architecture and implementation of these delayed view semantics with dynamic tables as the concrete representation of that, I'm wondering if you can talk to some of the database level primitives that are necessary to be able to implement and execute those transformations and provide the guarantees, however strict or loose they may be, that you are presenting in that theoretical framework.
Yeah, yeah. So I mean, there's many ways to slice the pie. I guess I can give you a quick overview of how we chose to do it at Snowflake. I already mentioned like the core thesis of what we were trying to do was make sure it's really, really actually part of Snowflake, and that is a double-edged sword. But I think it comes out very much net positive because Snowflake, it turns out, already has a very high performance columnar query processing engine. It already has a sophisticated optimizing SQL compiler. It has a very sophisticated metadata layer for or metadata and control plane for like knowing what data is in your tables and like managing your catalog and permissions and a whole bunch of like features that you probably haven't even heard about. And it also has a system for doing work in the background, scheduling work for you. And so what we did was we took those four kind of broad components. That is, I guess, going in reverse: the scheduler, which decides when things need to happen; the compiler, which will figure out like how to turn in your logical SQL statement into something executable; metadata, which lets the optimizer kind of do a lot of work; and then the execution engine, which will actually execute the plan for you. And we kind of extended them in very specific ways to enable the maintenance of views incrementally. And so what that means, I guess, to just kind of give one example is if you give us, for example, a join and you say, please maintain this inner join for me incrementally, the the plan to make that join be kept up to date incrementally is significantly more complicated. And we do a process that of algebraically rewriting the query plan so that if one side of the join changes, we'll like look up those changes against the other side of the join, and if the other side of the join changes, we'll look up the changes against the left side, and then we'll kind of apply those changes on top of the data that's stored in the dynamic table. And I say this as like the actions that we'll do, but what that will really do is produce a plan, which we then hand off to Snowflake's existing execution engine, and it'll just kind of do all that for us. And so we've been able to do all of this with a relatively small team and just like have it be part of Snowflake.
And so, as far as the workflow that enables, I'm wondering if you can talk to some of the ways that teams are applying this dynamic table capability and maybe some of the approaches that have been replaced as a result of having that as an option, where maybe they used to have to do a dbt incremental load, but they can actually just handle staging all of the raw data or landing all of the raw data in an S3 bucket via Kafka or et cetera, and then Snowflake can take over the rest just by virtue of having that materialized representation of that source data.
Yeah, yeah. So there's a few different aspects of this problem that are kind of solved by pre-existing tools. Like DBT is a good one to focus on because most people will know what DBT is. I guess it, in short, it's uh, I guess it's a nice Python library that lets you write SQL queries in Jinja templated form, and it will kind of execute them this graph for you, so you can kind of like build your pipeline out of this SQL. But the really important features I would argue for that DBT has is it has opinionation on your developer workflow, right? It lets you organize your files together. It lets you templatize them so that you can test them and you can instantiate them in different environments. And then there's this other half of its functionality, which I consider it's not developer time functionality, it's like runtime functionality, where it'll like actually invoke your DMLs to do the refreshes for you. And very often people will like have their DBT inside of either DBT Cloud or inside of an Airflow, or they'll be invoking it from somewhere, right? And so what Dynamic Tables does is it doesn't we haven't really tried to address the developer workflow half of that problem at all. It focuses purely on when like orchestrating the workload for you, which is like when do these refreshes need to run, and then automatically incrementalizing things for you. So you don't have to figure out what an incremental materialization is, or what are they called? Micro batch materializations? I can't remember. They have a new one that seems to be pretty popular. But Dynamic Tables kind of takes care of those two problems and then kind of lets you bring whatever developer workflow you want to the table.
Once you have a dynamic table as part of your overall analytical suite, what are some of the other ways that that changes some of the access patterns or data modeling approaches that teams might have typically used to address some of those complexities of constantly updating data? Maybe there's no longer a need to do a lot of complicated logic or joins within the staging layer, or maybe it changes the way that they think about the overall dimensional schema that they might use for their core warehouse layer. And just curious how that has impacted the patterns that teams build on top of.
Yeah, that's a good question. I think the hope is that well, I was going to say the hope is that it doesn't change what you're trying to build in the first place. Maybe, I guess, probably the biggest change from that perspective is it makes it much easier to build things that you wouldn't have built otherwise. But in terms of like, I want my dimensional schema, I want this warehouse kind of configuration, I want a data vault or something like that. The idea is to just be let you do what you want to do, but make it easier. The kind of key differences are, like I said, it makes it easier to do it, hopefully. So you can just like create these and then just let them go, right? Put them in a dedicated warehouse. I guess warehouse here in this context, I mean a Snowflake warehouse, which is basically a pool of resources, right? So you give it a pool of resources and just let it go.
And so, having this capability of managing the incremental updates, handling the complexities of ensuring that the different data sources are aligning in terms of the delivery cycles, it still doesn't address the other end of the problem of managing that input layer of how does the data even get to Snowflake for it to be able to do that incremental processing. And I'm wondering if you can talk to some of the ways that you're thinking about the automatics. Maybe it's an append only log, or in particular being able to handle things like deletions or updates as you are doing that processing, and just some of the structural patterns around this unbounded data and how it lands in the context of Snowflake for it to be able to then be fed into these dynamic tables.
Yeah, yeah. Yeah, so there are two aspects of this that I think are worth treating separately. The first one is the integration challenge. Like dynamic tables all lives entirely within Snowflake. So like how do you get your data out of Salesforce or whatever, right, in the first place? And that's kind of like the connectors land. And there's no, I guess I haven't seen a unified magical solution that just like lets you do that. I feel like it's just a matter of engineering and working through all the different ways that systems let you get data out of them. But there is an interesting kind of new angle on this, which is Iceberg. I guess, and more generally, like standard data table formats, right? Snowflake cares a lot about Iceberg in particular, but there's also Delta and Hoodie and probably a few others that are less popular. But the basic idea is there is if you can get everyone to agree on a unified table format, then everyone can export to that, and then everyone can read from that. And so Snowflake has been investing very heavily in Iceberg, and part of that investment has involved supporting dynamic tables that read from Iceberg. And so if you opt into this kind of iceberg way, this iceberg perspective on the world, then you more or less sidestep the data integration problem and you just use the iceberg table as your source. And you can even make dynamic tables be stored as iceberg. And so you can kind of use iceberg as your input and your output format and kind of do all your transformation in Snowflake, but make that transformation visible to anyone outside of it. But then there's the second half that you mentioned of like, what about the semantics? Like, what if your data actually needs to disappear? What if you have GDPR constraints and you need to delete stuff after some time, but you still want like your statistics, right? Like there's a very real problem with a materialized view where if you did a monthly aggregate and you delete the data for that month a year later, it just disappears from your materialized view. And so that's where, like I said, view semantics doesn't help you with that, but it's a very important problem. And so it's something that we are currently in the process of proposing extensions to. I guess we announced these features in June. It's like a suite of features that we call immutability. And the basic idea is you kind of start with view semantics at the core, and then you put a layer on top which says, make this portion of the table immutable, and like you can freeze it, I guess, and that the region that is frozen can kind of grow over time, and you can kind of like lock it in place. And what that ends up doing is it divides your dynamic table in two, where there's the immutable region, which is basically just a table. Like it originally kind of derived from some source data, but it stopped. You kind of broke that coupling at some point, and now it's just data. And then there's the other portion of your dynamic table, which is the view semantic portion, and that keeps getting refreshed for you. And that unlocks the ability to do things like control over your backfill. It lets you migrate pipelines from tables into dynamic tables. It also eventually lets you do things like watermarks that you do in stream processing. You can have control over which results you want to see and which results are now immutable or final. And so we think that that's kind of like the next big step to go beyond view semantics, but we're still in a preview state with that. So I don't have like a full description and documentation that I can point to people.
And then another element of the overall problem space is once you have landed all of your data, you've defined the view structure that you want to see and keep it up to date, is the problem of continuous data validation as the view gets updated, and you want to make sure that there are no violations of the semantic expectations that you have of the data, whether that's because bad data happened to get loaded in, or maybe there was a modification that doesn't match what your expectations were, but you actually want to keep it, and just some of the challenges around doing that validation and testing and evolution of that view as the business evolves.
Yeah, yeah, and having this validation in place is really important to make sure that you have actually good results in your pipeline. That's just like staying up to date for you, right? The way that I guess people model this traditionally in a batch system is you run a batch, then you do some validation on that batch, and then if that passes, then you kind of like proceed either down the DAG or to the next batch, and if it doesn't, then you alert someone, right? In streaming, things have always been much more complicated, I guess. There is this concept of a dead letter queue which tends to only really apply on a per event per row basis. Like, oh, I tried to parse this thing and I thought it was a credit card number, but it has a letter. So I don't know, just put it somewhere else and I'll deal with it later, right? And I think bridging these two is a real challenge, like a real design challenge. The approach that Snowflake is taking is to start with monitoring. We have a construct called a data metric function, which you can put on a regular table or a dynamic table. And what that does is it runs some function over your table periodically and exports the result into an event table, which is kind of Snowflake's telemetry object. And then you can kind of set alerts on that and say like, oh, if my left join, which I really should be an inner join, but I'm doing a left join just to make sure that I don't lose any rows. And if there's a null, that's actually a really bad sign. So I'm asserting that this column is never null, right? Then you can have an alert like, oh, this column is null. You should do something about this. Kind of the next step beyond that is intervention. Like before any of this bad data gets into the system, just like stop it or set it aside, put it somewhere else, right? And that's where we don't currently have any built-in capabilities to make that first class. But you can, I guess, the starting point is having the ability to do that, and you can build that logic into your dynamic tables already. You can have a dynamic table that kind of filters out the bad rows and only has bad rows. And if that table's not empty, then you know there's a problem, and you have the data right there. There's kind of like a whole, I don't know, it's a very complex surface area. So like integrating with tools like DBT is something that already works, but could be better. And so I think this data testing story is something that's going to kind of keep evolving over time.
Now that you have this more generalized framework for how to think about and talk about this use case of continually incremental updated views based on the changes to the source data, what are some of the ways that you think that other database engines could potentially implement that same style of capability? And what are some of the core primitives that would need to be in place before that work could really be feasible?
Hmm. So I guess like the general approach that I described of like if you have a database, you probably if you have a SQL database, you definitely have a compiler and an executor, and you have some metadata, right? And so at the very least, it's like not too big of a lift to implement some kind of incremental view maintenance. And I think like for example, the PGIVM extension is basically that. If you have some way of scheduling work in the background, same thing applies, right? Like you can automate the execution of those refreshes. I think the interesting questions come in kind of at the next level down, which is one really important question is usually you want some kind of isolation between your workloads, right? Like these kind of asynchronous delayed workloads, usually you want to keep them off to the side from your interactive transactional workloads because if suddenly you do too much work, you don't want your serving layer to go down, right? And so depending on the architecture of your database, this might be easier or harder. If it all runs on a single node, it tends to be pretty hard. If it's kind of like one of these cloud oriented systems where you have the ability to kind of spin up clusters on demand and for specific workloads, then that's much easier. And Snowflake was kind of one of the pioneers in this area, so we rely heavily on that to isolate workloads. Another interesting kind of complication is which indexing data structures do you have available to you? I mentioned earlier that if you want to do a join incrementally at, I guess, with relatively small batches, you really badly need an index. And so depending on, do you have a B tree? Do you have a sea of Parquet files with no metadata on them? That incremental join could look fairly cheap, or it could look like a full table scan every time.
And as you have been working through the implementation of dynamic tables and the formulation of the delayed view semantics framework, what are some of the ways that your perception and understanding of the problem space has evolved over that period?
Yeah, I really like this question. I feel like the general premise has held pretty true. The premise being incremental view maintenance is like a really clean, elegant way of thinking about kind of continuous data processing. And also, like I think anyone who really thought about it knew immediately like that's not enough. You need other things, right? So those basic things have held up. What's been interesting to realize is I guess how much of a gap there is between thinking in terms of view semantics and kind of the imperative batch oriented pipeline thinking that people had been implementing until now. Like it early on in the dynamic tables release, very often like it was hard to get people to wrap their heads around like no, it's just the result of this query. Like if you ran this query you'll get a result, and if you put it in the dynamic table you'll get the same result, right? And so that was an interesting kind of thing to get over. I think at this point we've seemed to have overcome the hurdle. I don't know if that's just Snowflake specific perspective. Maybe our sales team has gotten really good at explaining it. I guess another thing that's been surprising is how often people compromise on correctness. in order to like get done what they need to get done. Like if you do, for example, an incremental materialization in DBT, you're not really doing pure, proper, self-consistent incremental view maintenance. You're doing some facsimile of it that depends on a whole bunch of assumptions on your source data. And if you try to implement proper view maintenance on it, you're actually doing a completely different thing that might be much more expensive. But it turns out when faced with that decision, people want the cheap thing that is just approximately correct. And so I think it's even going beyond there are things that view semantics can't express. It's realizing that those things that view semantics can't express are things that people really, really need and really, really care about. And staying kind of in the pure abstract model doesn't actually get you there.
As you have been building and evolving the dynamic tables functionality at Snowflake and evolving the framework for how to describe and talk about it in the absence of the technical representation, what are some of the most interesting or innovative or unexpected ways that you have seen that feature set applied?
Yeah, I think what's been especially interesting has been to see people mix and match Snowflake features. I guess, from the perspective of dynamic tables, like very early on, like from the start, dynamic tables were just a regular schema object that had regular RBAC. We supported replication very early on in the life cycle. And we also supported column masking policies and row access policies. And these are like relatively common features in databases, but extremely uncommon features in streaming systems. But they ended up being, because we were so close to the database, they ended up being like basically like table stakes features for a lot of customers. But what's been interesting is to see how that manifests in the use cases. Like we have customers that they stamp out thousands of instances of approximately the same pipeline over and over and over again. And so they end up needing to manage like 100,000 dynamic tables in a single account. We have other customers who, I guess, durability and disaster recovery are really important requirements for them. So they will replicate their entire dynamic tables pipeline into another Snowflake deployment, and they expect it to just kind of work. Like if they do the failover, the pipeline should just keep working, and it should read from the source data in that other deployment. Another instance of this is Iceberg that I mentioned, like letting people read and write to and read and write from and to Iceberg has made it like really easy for people to just like kind of work in their data lake more easily than they would have using other tools that are kind of harder to pick up than Snowflake.
And as you have been building out the technical functionality and exploring the overall problem space of dynamic tables and delayed view semantics, what are some of the most interesting or unexpected or challenging lessons that you learned in the process?
I guess one thing is how hard it is to actually get the right result when you're building infrastructure that's supposed to compute something. I think like a lot of the time when you're building a system, you actually have no way of determining whether or not you have the right result. Like you kind of like if your system computes something, then in order to check if that's correct, you need to compute it some other way, right? And a lot of the time you just don't have another way, right? But the nice thing about view semantics is you do have another way, right? You have the view that you can run, and you have the dynamic table that should produce exactly the same result, assuming they kind of start with the same underlying timestamp. And so we actually have taken this very seriously, where we basically built in runtime asserts into every single dynamic table refresh. That it's not 100% coverage, but it's quite good coverage that our incrementalization didn't do anything wrong. And if it does, it will fail the refresh and send an alert to our team, and one of us will have to debug things and investigate and figure out what's wrong. And it's been like completely fascinating, both to see how easy it is for us to get something wrong. Like I mentioned, these algebraic rewrites. Like if you rewrite an outer join and you forget that this column, if it happened to be nullable, then you need to propagate that nullability, or you need to not propagate that nullability. And like there's all these like really nuanced contracts inside of SQL that are hard to keep track of. Oh, one that I learned is if you do a scalar aggregate without a group by, you're always guaranteed to get a row, even if there's no input. But if you do a group by, then you might get no rows if there's no input. And so it's little things like this that can really get you. But by having kind of this property based testing of where we have a system that automatically generates queries and then it'll make a view, make a dynamic table, compute them on the same timestamp and compare them, we've been able to catch a ton of our bugs and also a ton of like weird random corner case bugs that existed in Snowflake for like 10 years and nobody had ever caught because they had no way of catching them.
It's definitely interesting both the ways that long running systems can accrue those types of hidden problems that never raised to the level of being caught or addressed, but are actually problematic in those weird corner cases. And then also the fact that SQL as a language and as a specification has been around for so long and yet still has so many uh, weird and quirky behaviors.
Yeah, it's funny because it probably just keeps accruing the weird and quirky behaviors over time, even though one would hope that these like weird corner case bugs get hammered out over time. So it's yeah, things are kind of moving in opposite directions, and the net is we have to keep squashing them over time.
It doesn't help that ANSI SQL as a specification is actually more of a recommendation than an actual spec, and that everybody who builds a database ends up evolving the actual SQL semantics to fit their use case in slightly divergent ways. And sometimes that gets folded back into the specification that people can then reinterpret in their own manner.
Yeah, yeah. Actually, it's funny you mentioned that because there was like a subcommittee of the SQL standardization committee that was focused on standardizing streaming SQL. This subcommittee ran from like 2021 to 2023, and I was on it. I ended up chairing it by the end, but it was so hard to get any consensus because everyone just had their own like, oh, here's my extension and here's what it does, and like here's my extension, and obviously we had our own extension, but we hadn't actually even implemented our extension. And so we ended up having to put a pause on that effort because we need at least like some solution to become like the obvious thing before we try to make it a standard.
Design by committee is always an interesting problem.
Yeah.
And so, for people who are working on this problem space of trying to do a continually updated view over some set of source data, what are the cases where dynamic tables and or the delayed view semantics theoretical framework are the wrong approach?
So right now, I guess speaking specifically, okay, so delayed view semantics, I think I already spoke to that, right? Like there are cases where you just can't use view semantics. We have our guess, our take on what those extensions should look like, but there are other things out there, right, that can try to do that. In terms of what dynamic tables themselves can and cannot do, I guess so. We are definitely focused on the analytical use case. We're not focused on transactions and kind of interactive serving as well. I mentioned that our architecture is focused on higher latencies. Like we just went into a preview with 15-second lag for dynamic tables, but there are systems that are optimized for 100 millisecond lag, right? And dynamic tables just aren't optimized that way right now. You could see a future. I guess the nice thing about the programming model is you can swap out implementations under the covers, and so that's not necessarily a future we won't head toward. But right now, true low latency streaming is not what dynamic tables is for. It's more about doing reasonable, or I guess like I would say like typical latencies that are really easy to do directly inside of your data warehouse.
And as you continue to build and iterate on the dynamic tables functionality, as you continue to think about what that specification for streaming SQL should look like, and as you continue to popularize this idea of delayed view semantics, what are some of the things you have planned for the near to medium term, or any particular projects or problem areas you're excited to explore?
Yeah. So a few, I guess the area I'm most excited about right now is immutability. We have a couple of features in private preview right now that will be launching to GA, I think at the end of this month. And so we'll be, posting about blogs, but I think that really kind of expands the addressable market of dynamic tables massively because suddenly you're not constrained to what you can do within a view. But we're also doing a whole bunch of other things. Like we're significantly improving our optimizer and our incrementalization engine to be able to handle kind of more complex queries and break them down into pieces and build indexes and kind of do a more sophisticated set of things that are more in line with what a very mature database can do rather than like a scrappy project that is just a couple years old, right? We're also kind of continuing to build out new features. Iceberg integration is a really important one. We already have basic support for Iceberg, but Iceberg is moving really fast. The V3 spec came out a few months ago, and so we're racing to reach conformance with the V3 spec, both on read side and write side. And it'll actually be pretty exciting because the V3 spec has something called row lineage, which makes it much cheaper and actually possible to do CDC on an Iceberg table. And so our team actually drove a lot of the standardization of the row lineage spec, and we're going to be implementing it in Snowflake as well.
Are there any other aspects of the dynamic tables implementation and the overall work that you've done around the delayed view semantics framework that we didn't discuss yet that you'd like to cover before we close out the show?
No, not really. I'm just pretty excited because it feels like we're finally getting to the place where stream processing is like, it's like a mature discipline where we've actually explored a fair bit of the problem space and we have a lot of good solutions. And hopefully we're reaching a place where we have a common language to talk about all those solutions as well. And so I think it'll be really interesting to see which problems crop up once we're on the other side of those.
Absolutely. Yeah, I can definitely recall in the early to mid 2010s when stream processing was first starting to become in vogue with things like Storm and Samza and the early days of Flink, and everybody was doing their own thing. Everybody had different approaches to how to think about it. And now I think, as you said, we've hit a point of maturity, both in terms of the operational capabilities as well as the ecosystem's understanding of what are the actual technical problems to be solved and how to address them, so that I think that we can start to reach that next level of capability and therefore enable broader adoption without it just being the most technically advanced teams who have the capacity to even conceive of adopting stream processing.
Yeah, totally agree. I mean, that's ultimately the hope, right? Like, I think the way I phrased it when we were first starting the Dynamic Tables project is our goal is to make the streaming paradigm easier to use than the batch paradigm, right? And if people are building 12-hour freshness pipelines out of Dynamic Tables, you'll know that we've won or we're doing that, right? So I think we're really on the right track.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think what it comes down to is sprawl. I think there's just so many tools out there, and you kind of like, they're necessary tools a lot of the time, right? Like, most customers that we work with have, well, they'll have their transactional database, they might have their Spark pipeline, they'll have their Snowflake, they'll have their Prometheus. There's so many things. They might have their search index, and there's so many kind of purpose-built tools that each do kind of a specific thing, and they do it well, certainly by now. But if you look under the covers, like as an infrastructure engineer, it's kind of infuriating to realize that all they're doing is mix and matching the same things over and over again in slightly different ways. And I feel like the biggest gap that I see is a cleaner, more unified way to mix and match those kind of core primitives that are underlying all of these technologies, so that we can reconsolidate all the sprawl and the mess that we've gotten into, the wiring of dozens of different systems just to get your basic website working. It would be magical to reach that point. And well, I hope that we can hit it in the next few years.
Absolutely. Well, thank you very much for taking the time today to join me and share the work that you've been doing on the dynamic tables feature at Snowflake and the formalization of the delayed view semantics framework. It's definitely a very interesting problem area, an interesting approach to a very real technical problem that people are addressing. So I appreciate the time and energy that you're putting into that, and I hope you enjoy the rest of your day.
Thanks a lot, Tobias. You too.
Thank you for listening, and don't forget to check out our other shows. Podcast.net covers the Python language, its community, and the innovative ways it is being used. And the AI Engineering Podcast is your guide to the fast-moving world of building AI systems. Visit the site to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story.
And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.